Hey, what's up YouTube? Back again. So here we are. I think we're on day 11, 12. Just a little recap from yesterday. We downloaded some of the Java code that is inside the program object in the vibecoder repo for the quadratic model. We copied it into Python and kind of built our similar little loop through our data structure. So this was actually just mimicking 4 days of data, where this first number would be the delta t's from the zone temp and occupied set point deviation, and then this is supposed to be minutes. So yeah, this was kind of cool. So basically we loop through our saved data and we come up with these some x's, some y's, some xy, and then also this x squared. So kind of brute forcing your way through the data, sum up all that stuff. Then we come up with this beta and alpha parameters, which we're still looking at today. And then we fitted a line so that we got our equation. So this was our fitted equation, and then we calculated some fake minutes. So yeah, so it's kind of interesting. So like the worst case scenario was 40 minutes with a 7-degree delta, and then we attempted, so this was 12-degree delta here, and then our model output 63 minutes. So I guess that seems kind of legit, I guess. So maybe we could even play around with this a little more. So I'm sure we'll kind of build off of this. So we could just say one day we had 12, which was these guys. And how about our actual time? We can just say 65, just making something up. Okay, so that's our current Python code for the quadratic model, and then this was what we copied from Java World. So I was really curious yesterday what this was for in our AI generated code, but I think it's actually doing something where it's checking that if our model is kind of coming up with something like too small, like it's not generating very good data. It's just kind of like a safety factor that if this denominator coming up with this is just like a safety checker by length of how many days of data, the sum squared. It's kind of interesting how they come up with that, but it's just actually putting back in the default alpha A and alpha B parameters, so it's just like a safety check. I was kind of curious about that yesterday, so I'm just going to delete that out of there for today. And I think that we already basically did this. Just like get back into day 11. So let's just read through this. I think we'll skip over this. But goal, fit straight line through noisy data without statistics. Regression finds a line that minimizes the squared vertical distance between your data points and the model for a simple linear relationships y alpha bx. The ordinary least square solution has closed form expressions for the slope and intercept. Wikipedia gives you the term alpha beta in terms of sums and y's. You can implement these formulas in Python directly. So yeah, I think this is just a review from yesterday, and we basically did this. So we have a little data structure. We're doing this math in a little more beginner-friendly way than these confusing things. And coming up with the alpha and beta with the same equation, which we talked about. Coming up with the fitted line. So explain why the code, use the code. Okay, so maybe we did this yesterday, but this is just a review then. Explain why minimizing squared error is preferred over absolute error. I thought that was kind of an interesting question. How would adding more noisy points affect the slope and the intercept? So I think like this first question is squared error, that if there's really an outlier, that the model will kind of that it'll help. So like the trained model parameters will help minimizing for squared error, but I think it's really confusing because we're not actually using it, so I don't know why they're putting that in here. Versus minimizing for absolute error, at least in machine learning, I think that you'll get better results if you're minimizing for squared error, because it will kind of smooth out any real big outliers. Seems kind of funny. I think I might skip this and jump right to the next one, which is day 12. Okay, day 12, manual math. So apply ordinary least squares to compute model 1 parameters. Given this a series, the delta squared t pairs, so this is our delta squared and then our minutes pairs, you can compute the optimal alpha A and alpha B using the same regression as day 11. Here x equals delta time squared and y equals time. The resulting coefficients minimize the sum of squared errors between the quadratic and the data. Writing out the sum by hand reinforces the algebraic process. Apply the concepts using a formula algebra to refer to them in an example. Understanding this concept allows you to build more accurate energy efficient optimal start models, improving comfort and energy savings. So here we have some fake data, looks familiar. So they're just coming up with this, basically they're just, the x's equal delta squared, so they're just squaring all this data and they're coming up with another little data structure, and this is the same as this. So they're coming up with the same stuff that we've been talking about, and then they're just kind of printing like a new little equation here, which is kind of neat because they're describing the alpha A parameter with units, so it's minute per degree squared, degrees Fahrenheit squared, and then this is also just in minutes. So I kind of like the units. It helps me wrap my mind around some of the data. So I might just actually copy that print statement. I think it's a better print statement than just looking at the line. I think this would be the same as, I think it should be the same as doing this and doing this. So if we printed this again, so this is what our model is coming up with. So it's coming up with 3.45 minutes per degrees Fahrenheit squared, and then also alpha B is coming up with a constant of 5.1 minutes. Interesting. Maybe we could just do a little, let's do a little, make our prints nicer. Minutes, and I think like we could even do this. I'm just gonna cheat to do the round round method. Oops, hold up, I'm trying to do this round function here. Now the way that we could write this is in like this kind of notation, where it uses an F string in Python. So that's kind of like a fancier, more modern, the pro way of making print statements is using F string, which I think stands for Fortran string. Okay, so minutes, I'm just gonna make this look a little better. Put a quote in here. And oops, let's see, what are we missing? Single quote. So these F strings, I think, are a little better way of doing this, fancier way, the pro way. And we come up with the same thing. It's just actually doing a floating precision of 2, which did the same thing as round, but probably a little bit more fancier. Okay, so where were we? So day 12, choose your own delta t pairs and compute x. Okay, so we did that. Verify substituting computed coefficient. Verify that substituting the computed coefficients into t reduces the error in your data set. Verify that substituting computed coefficients reduces the error. Why is this important to use several days rather than a single observation? I think that this is because we just need more data. Generally thinking, like, the more data, the better your results will be. The paper, PNL paper, recommends using 14 days of data. So this little data structure would be 14 days long, and we only have 5. I'm still kind of like hung up on this. Verify that substituting the computed coefficients reduces error of your data set. I don't get that. So let's go ask for ChatGPT. I think this was what we were talking to ChatGPT yesterday, so it might even have, I'm just gonna give it the math lesson again. So we are on day 12. Yeah, day 12. Okay, I'm just gonna say, whoops, what does that mean? And then maybe give it my data set. Be like, am working with this. All right, let's see what AI has to do. I knew we would get into some harder concepts, and I need a little bit of a tutor here, so why not ask AI? Okay, it means take the coefficients you just learned and plug them back into the model. Generate predicted times for each point, then compare the predicted. Oh, cool. Neat. Okay, so I think that's what they're doing here. So, this is kind of cool. So basically, they're asking us to, okay, so let's see if I can do this the same way. So we did DEN. What the heck is DEN? Denominator, I guess. this the denominator thing that we were asking about in so that's the same thing we were asking about in the Java code, like what the denominator is. Same thing I was asking at the beginning of this. So they're just saying like not enough variation in the delta squared to fit model 1. Okay. And then that'll just end our program actually. Okay, so we have some x squared. We're calling these different variables here. And then n is days. Come on. All right, so we passed this test. If this test failed by not enough variation in the temperature or delta temperature squared, the program would exit early. So what else do they do here? So we solved this alpha A and alpha B. Hold up 1 second. Let's just see here. So we do have like a little bit different coefficients here. So n times, I'm looking at this right here. Maybe I'll just put this over here. That's right here. So put them side by side. So alpha A equals, or alpha B. Or maybe I was kind of screwing this up a little bit. Slope and intercept. All right, so let's just make this the same as they call their variables a little bit different numbers, but so this is alpha A alpha B maybe I'll just get rid of this. Okay, so alpha A was some y minus alpha A times some x divided by days. So I feel like this screwed up. This is actually alpha B. So alpha A equals, I'm just going to copy this. This would be here. Copy, paste. Okay, so alpha A, let's just double check this. This is days, denominator. All right, So model 1 print. Let's just run our script. So it does. Here's our equation. All right, so this is the model error, which is interesting. So all right, actually, sorry. Mean y equals sum y divided by n for days. So I'm right here. SSE, what they're calling SSE. Let's ask AI, what does SSE mean? I think it's standard error. Sum of squared errors. Okay. So let's just say all these acronyms. SSE fit equals 0, SSE mean equals 0.0. So we could do for delta t time in data. Same thing as our little for loop up here. We're for looping through it again. So x equals delta t times delta t y hat, kind of interesting, equals alpha a times x plus alpha b. Error of the fit equals time minus y hat. Error mean equals time minus mean y. Whoops. SS e fit plus equals error fit times error. Well, so they're just adding up all they're multiplying the error here, squared error, adding it together. Kind of makes sense when I type it all out manually, somewhat making sense. Plus equals some more kind of squaring some error. Whoops. Come on. Times error mean. Alright, so I'll just cheat a little bit right here, copy these guys. Alright, so here we go again. So we have some, I'm just looking at our prints here. So this is our data. We for looped through it twice. Our first loop, we came up with the equation, which is basically the meat and potatoes is these parameters right here, alpha A, alpha B, and then they're defining x. X is our delta t squared, which is our units here. So I just have to sit and think about this for a second on where x originally gets defined. it's right here, I guess. So yeah, that makes sense. And then they're actually comparing yeah, so we're just like, we're looping through this and then computing errors for each one of these. So error in the fit. And interesting. So fitted model. So I just need to take a second to kind of soak this in. So yeah, it's just the squared error. Cool. So this is error in the fit, error in the mean. It's interesting. We did two. I still have to soak that in on squared error on the fit and then on the mean. I'm going to ask AI. Okay, the denominator question. No statistics required. Well, I guess what I was kind of curious to say, why are we taking error twice? Why are we taking error twice? Once on the fit and again on the baseline mean. Okay, let's just see what AI came up for this, and then I think it's good enough for one day. We compute two errors because SSE by itself has no meaning unless you compare it to something. Okay, that makes sense. So is my learned model better than doing nothing at all? So baseline mean model, that makes sense. You need something to compare it to. This is why the error, you don't learn anything. It always predict. Okay, so this answers, if I ignore delta t completely, how wrong am I? Doesn't really make a lot of sense. So I think we'll kind of build off of this a lot in the future though. So cool. So I'm just going to paste that into ChatGPT and maybe ask it to comment on those error prints for what you said. All right, here we go. Perfect. This output is actually very useful because it reveals a specific bug, not a conceptual mistake. Your regression math produced using different x variables. Oh, great. So what you predict telling you got the learned model is 275x worse than doing nothing. Okay, so maybe we have a little bug here in our data. Okay, so maybe like when we, okay, so I think we have to like basically reset our parameters back to 0 when we do this. I think that's the bug. It didn't look like it solved anything. I'm just gonna ask it, where is the bug? Nothing like learning, right? Your bug is in your first for loop regression sums. So you're telling the code these 3 lines. All right, maybe I'm getting something mixed up from our previous lesson here. Replace a regression for loop with this. I'll just have it sound. Can you provide a completed script? I'll have to study this a little bit and then maybe make sense of it again for tomorrow's lesson. Nothing like having a nice artificial intelligence teacher here. All right, so I think I'm gonna stop here today and then probably spend a little bit of time soaking this in, and then we can chat about it tomorrow. So cool, this is interesting stuff. I'm really excited to get into the machine learning side of things, which I think is like way later in the lesson plan. Hopefully I get that far, knock on some wood. So this is cool stuff. So hope you guys are liking it. Provide a comment if you see anything, anything out of the ordinary you would like to elaborate on a little bit more, but I'm enjoying it so far, so I will continue. See you guys tomorrow.